This is a video tutorial on how to calculate a mixed effects factorial ANOVA with one fixed factor and one random factor. We're going to be using high school and beyond data set from SPSS. Our dependent variable will be reading score. Our fixed factor will be socioeconomic status, SES, and our random effect will be school program type. We can look at the variable view and we can see that school program type is currently listed as general, academic, preparatory, and vocational. We will treat these three types of school programs as a random sample of possible programs within a school setting, and we will be trying to generalize to whether or not there are differences within the population of potential values for school program. To run the analysis, we go to Analyze, General Linear Model, Univariate. We send reading, standardized reading test to the dependent variable. The fixed factor, as we said, is going to be socioeconomic status. Our null hypothesis in this case is that there is no difference in population means for low, middle, and high socioeconomic status in terms of standardized reading score. We will send school program down to the random factor. Our null hypothesis in this case is that school programs account for no variance within the population. Another way of saying that is that the means for all possible school programs are equal within the population in terms of standardized reading score. We click on plots because we're interested in seeing whether or not there is an interaction between school and program. So we are going to run separate lines for each program, and since socioeconomic status is an ordinal variable, it makes sense to use it as the horizontal axis. We click that in order to get a plot of the interaction. We click Continue. We're going to run post hoc tests for SES. You'll see that it doesn't even offer us a post hoc test for program because we are treating program as a random effect. So for our illustrative purposes, we will click just on the Chaffee and click Continue. We'll go to Options and we will select, we'll send overall to the display means so we can get the SES program and interactions. We'll click on descriptives, homogeneity tests, and estimates of effect size. Click on Continue, and we will click on OK. This will provide us the analysis. We can see that we have the descriptive statistics for each level of socioeconomic status and the means within the three sampled values for high school program. We see that we do not reject homogeneity of variance assumption because that value of significance is greater than 0.05. We see our hypothesis tests here. Since our alpha level for SES is greater than 0.05, assuming that our alpha was set at 0.05, we would fail to reject the null hypothesis that the means of SES, the means of reading, were equal for all three levels of SES in the population. However, we find a main effect for program, which tells us that some variance in reading scores is explained by program type. That means that we would reject our null hypothesis that all possible program means for reading are equal within the population. We would fail to reject our assumption, our null hypothesis regarding interaction between SES and program. We can go down and we can look at the post hoc test to understand where the differences are, and we see that for SES, even though our value here was greater than 0.05. The post hoc tests indicate that there were some differences. Our profile plots um, move around a lot, but again, because we're not interested really in making a conclusion to these three programs, this interaction test is just illustrative. The other thing that we need to do with this data is we have to also run a variance component analysis, and that variance component analysis will look just like the analysis we just ran for the mixed effect factorial ANOVA. To do that, we once again send reading to the dependent variable, SES to the fixed factor, and school program type to the random factor. Then we just click OK. And what this will give us is all of the variance components. So to understand how much variance is accounted for by all possible values of program, what we do is we add up all three of these estimates, and that gives us our denominator. And then we would divide 19.629 by the sum of these in order to get the proportion of variance that is accounted for by program type.